last time what we discussed is that the two-dimensional arrangement in the crystal systems. Then we went to the three-dimensional arrangement, okay, where we have learned the two types of voids. One is the octahedral void and one is the tetrahedral void. Okay. Now let's take a quite extent of the three dimension. Okay, let's say last time what we have learned for the two layers. Now if there is such a case, there is more than one layer. Okay, so first layer and second layer what we learned last time, and we are adding another layer, that is the third layer. Okay, and more on. Okay, if I add, okay, so if I add more on, then what will happen? It will be the repetition of these three units. Okay, so let's say that can be categorized into two cases. Okay, in first case, what can happen? There will be a lattice arrangement where there will be one octahedral void and there will be one tetrahedral void. Okay, such cases. So what I will have here, one triangular plane where it has contains 3 atoms in a plane. Okay, and then after that plane, next plane, you have a 6 coordinated system. Okay, if you combine this, then what will happen? You will find this central, this atom and this atom, they make here a tetrahedral void. Okay, whereas you will find if this 3 and your this this 3 and your this 3 will make a octahedral void. Okay, so what I am doing, I am just joining the joining the lines which should pass through this. Okay, so if you see here is that the tetrahedral void is passing through the center of this atom. Okay, in the same case the tetrahedral void of this is passing through this center atom, whereas this is the octahedral void, right? This is the octahedral void. This octahedral void will pass through these atoms. Okay. So there will be a consecutive tetrahedral void and octahedral void, tetrahedral void and octahedral void, tetrahedral. It's a sequence. Okay. Now, if there is number of atoms in that lattice is n, so as we know from the earlier, the number of octahedral voids will be n and the number of tetrahedral voids will be 2n. Okay. Later on, I will tell you that how to determine the formula of a crystal or solid compound using this concept. Okay. Now, in this case, what is happening? So we are getting a consecutive A. If we say this tetrahedral is A, this void is A, and this kind of molecular hexagonal arrangement is B, then it's a AB type crystal structure. Okay. Now this kind of crystal structure you will find is that it's a forms a hexagonal structure. Okay, it's a hexagonal structure, and this sort of arrangement of this three-dimensional crystalline system is called hexagonal closed packing. Hexagonal closed packing systems, or in short, it's known as HCP crystal arrangement. Okay, so this is what is the type AB type. Okay, acha. So now what happen if the two tetrahedral voids are consecutive with each other? That also can happen, right? The two consecutive and the two will be esteemed by two hexagonal packing. So what will happen in this case? So in second case, what I have done here, what this suggests that the two octahedral voids and these two tetrahedral voids, the octahedral voids are far and tetrahedral voids are near to each other. See, what I can do here is that this is the central atom, and this central will pass through this tetrahedral void, and it will so on. Whereas this octahedral void will pass through this atom and this void and then this atom in this way. So it falls in a consecutive line. Okay, it falls in a consecutive line, that one void corresponds to here an atoms. Okay, and this void corresponds to this atom. Okay, so it's kind of, if you go to the previous lecture where I have tell that this octahedral void are tetrahedral voids. If you find them from above, you can see the according to the arrangement, if there is this kind of arrangement, okay, this kind of arrangement, so this forms a tetrahedral void. And if there is this kind of arrangement, okay, this kind of arrangement, so it forms a octahedral void. You will find this is in normal NCERT book or any of your ISC book, you will find. Okay, acha. Now what here, if I combine this all the lattices, okay, acha, first let's combine this. So this is what the first type. What is a type? This is B type and this is B type, this is A type, and since it's reverse, so I am naming as a C type. If I combine these two, let's say in crystal, if I combine these two, what will happen? So it will become a Ca type. Okay, Ca type. That means, okay, see, this is a same one thing, one. Okay, I have just written this in a separate way. This is one. Okay, so it's a Ca type. Okay, if I say the Ca type, that means these two and these two will be overlap each other and giving the two rest part. So it's a square lattice. Okay, it's a square lattice. First remember that two-dimensional, it's a square lattice. Okay, I can do it. Okay, now if I combine everything, what I will end up with, very beautifully, I will end up with a cubic crystal. Okay, I will end up with a cubic crystal. Now, cubic crystal. Okay, so this kind of arrangement, what is called? This kind of arrangement is called A. Okay, I will write here as a, since I am defining this hexagonal unit as B, so I will write is B, C, A, B type. See, every cases, if anyone tell you in exam that to define the crystal, so what you will do, you will say that this AB, if you define, see very carefully, whatever you define, if you define this hexagonal unit as A and this tetragonal unit as B, so you will write B, A, B, A type. But you should mention, very carefully, you should mention that what type or which one you are designating here. Okay, very careful. Since I am designating the hexagonal unit as B and the tetragonal unit as A, so I am writing as a BCAB type lattice. Okay, now if I combine this, what I will get? I will get a cubic kind of crystal, and that's why it is known as cubic closed packing system, or we know it as a CCP kind of lattice arrangement. So this is HCP. So what I got? HCP kind of lattice arrangement and the CCP kind of lattice arrangement. Okay. Okay. Now I have a small model here. So what it end up with? See, if I combine, let's say, if I combine this 4, this 1, 2, 3, 4, 5, see, it will face the first layer. This is B, layer B. In this layer, see, 1, 2, 3, 4, 5, right? So this 5 is basically 1, 2, 3, 4, 5. Let's do a like this, maybe here, and let's say here. Okay. So this is in another unit cell is forming the center of the first what is that called, plane. Okay, face. So center of another. So I am not thinking about this part. Okay, so it's only 1, 2, 3, 4, 5. Okay, so this 5 is the first layer. Okay. Next layer. So next layer is this 1 2 3 4, 1 2 3 4. It's all are in the center of the faces of the corresponding face. Okay, center. And next, same layer B, see 1 2 3 4, the 4 edges and the 1 faces. So this has become very interestingly an FCC type lattice. FCC type lattice. Okay, I have a model here. Let me show you. Okay, so this is why I made this. Okay. Acha. See, this is a copper crystal I am trying to, because it's a brown colored arrangement I have done. So you see, if you see portray in this way, think. See, this is the first B layer. B layer. Hexagonal units, B, here will be 1, here will be 1. So it's the first B layer. Then what you have? You have a tetragonal layer, which is the CA type, the next one, this one, the CA type, right? Okay, and next at the end what you have? You have a same hexagonal, that B type lattice. So it's indeed a FCC lattice. So the CCP cubic crystals packed structure, which is a BCAB type arrangement, finally ends up with formation of the FCC lattice. Okay, acha. Now let's say what I'm trying. So let's say if you have given some information about a lattice, let's say if I give you information of a lattice, okay, and that lattice says that it's formed by two elements. Okay, two elements. What is one element is X, another element is Y. Okay, now in this case the number of voids, okay, is given. Number of voids, number of voids. Okay, let me reframe the question. Okay. It's given that a lattice is formed by X and Y. Okay, now this lattice makes a CCP type arrangement. CCP type arrangement, that means a cubic structure. Okay, acha, where the X is the cation and Y is the anion. Okay, acha. Now if they have given that Y makes the CCP, okay, and X, what X does? The X occupies octahedral voids. Okay, so what is the question? Let me tell you, write down the question. The question is a compound or a lattice compound, okay, it forms a CCP type crystal arrangement, okay, where the X is the cation and Y is the anion, and Y makes the CCP arrangement, that means all the atoms here which makes the CCP arrangement is Y, okay, and X occupies at the octahedral voids, means these are octahedral voids. Which one is octahedral void here? This one is octahedral void, this one is octahedral void. This octahedral voids is occupied by X. Okay, acha. So it can be bit of like a quite means it's very difficult to imagine, but just think it normally. Let's, when we meet, okay, when we will meet, you just ask me this question, I will repeat this, or I will discuss this once again. Okay, just let me be with, let's be with me. So this is the question. Okay, so X occupies the octahedral voids and Y occupies the CCP structure. Now the question is that what will be the formula of this compound? Okay. Achha. So what we know, if the N with the total number of atoms in the lattice, let's say n be the total number of lattice in the system, then the number of octahedral voids is n and the tetrahedral voids is 2n. Clear? So x is basically n, right? Okay, that means x is basically n and number of atoms, total number of atoms which actually makes a CCP structure, that will be the number of atoms present in the lattice. Clear? So this will be also equal to y, right? So what will be the ratio? X is to y is 1:1, right? So what is the formula? XY. Okay. Okay.